So we're going to go through fairly quickly several topics here where we aren't going to do design problems. And so each year this class, you have one topic officially left at this point, but we originally had notes and keep them in the packet for some more advanced topics here. And this is similar to what, in concrete and steel, we don't do a ton of lateral design. We did a little bit here with the column piece and the basic stud walls. These are in your packet. So if you go out and practice and you need something to refer to for this more advanced part of load of wood design, this is here. I will say that the Wood Association actually has a lot of free um, design seminars that you can also tap into, which are really good, particularly if you've had some of the like we've done the basics. And so you're in a position where you can easily go into those. They're made more for someone who's already practicing engineering, who's just not as familiar to wood. So those are handy to find as well. I'll go ahead and put that link in a place on our Canvas site. All right, so I'm literally going to flip through and hit some highlights on several topics, and then we're going to do, and you'll notice I didn't do the final example for combined bending. And I don't always do all the examples because some of them are very repetitive. All right, so lateral loading. So this is just when we have a building. Oops, let's do this to a light color. All right, so if we have a building and we look at it in this direction, no matter what kind of building, couple stories, what have you, we know we have all the gravity load piece. This is the column axial. This is the piece for bending of all the beams, and we looked at some of the lateral loading on the columns as a bending component, right? But if you start looking, and with wind, if you start looking at seismic or heavy wind, each building has to have something that resists that lateral overturning force. So we call everything that's going this direction basically as a gravity load. And then the rest of the loads are these lateral loads. Or if it's coming from the side, we resolve it into a horizontal and vertical load. All right, so these horizontal or lateral loads have to be dealt with. And there's a couple ways to do that. If I'm looking at a steel building, for instance, the two basic ways are to have, well, the main basic way, if you're only doing steel, is to have moment connections. And so when I go to push this frame over, it can resist that. So if you think of a frame from structural analysis that you push over, it does this sort of thing, right? If these were pins, that would not be a very, well, if it's all pins, it would be unstable. But you need at least some of these moment type frames, or you need like a shear wall, right? So this might be a concrete wall. And that wall, if I look down on the building, so I'm looking down on the building now, just at column grids or what have you, right? So when I look down on the building, if I'm pushing from this direction, um, it's this. I could put a wall in here, maybe by the elevator shaft, and you will go through this stuff in your senior design to some extent because you have to have something to hold the building up laterally. This could be a concrete shear wall, it could be a moment frame, or the other choice for steel is a brace frame. So I might have just here, and all of that load has to funnel through the rest of the frames and the floor or the diaphragm to get here. And those, you make as much of this as you need to take that full lateral force. Okay. In wood buildings, we also can have a shear wall like the concrete buildings, right? It's a kind of like what we looked at for the stud wall, but a little heavier duty. So let's just talk about lateral loading in general. We're not going to go through finding lateral loads, and actually we're not going to go through any of this in detail, but what we'll call this is the main wind force resisting system. So you'll see this acronym in some of the descriptions on wood, and that's wood does okay up to a point in earthquakes because it actually can deal with energy dissipation. But of course, in all of our undergrad classes, we're just looking at basically wind force as our lateral load. So what I just showed you at the start of this discussion was that, figuring out what your structural assemblage of elements is going to be assigned to provide that support. How do you get the forces there? And then how do you design to resist that? So when you have just cladding, architectural type components, that's not part of the wind resisting system, even though it may look to the casual observer like a wall or a shear wall. Um, those components on the side, however, they capture that load and then transfer it into the structure and into the lateral force resisting system. All right. So we're going to leave this piece alone. You can learn through the ASC 7 to deal with wind loads. And you talk about this in steel, I believe, a bit, and also in your structural systems class. So here we are, and now I'm looking at, and this is showing you exactly what I showed you on the first page. I got ahead of myself, but some bracing, some moment frames, some shear walls. You'll often see kind of in this lower picture where you see like the elevator tower going up first and then building around it. That's because that's the concrete shear wall system. Here is a good picture showing some heavy duty moment connections. Okay, and here's a shear wall in wood. Okay. And you notice that it's got to really be tied in here to deal with that. Wood floors and shear walls use plywood or OSB to transfer those forces. Okay. If I look at this simple wood building here, these forces on the outside would come through the cladding into whatever the lateral resisting system is, right? So this is looking down. Somewhere I have to have that lateral resisting system, and they'll show you in each direction. All right, we're not going to go that's through the structural piece. Let's look at what wood products look like that. We can have some heavy duty panels, composite panels, plywood, OSB. You guys have used this in probably home projects or building projects, or you've seen it in the lab for form work, et cetera, right? As it even says down here, concrete form work. We've talked about the different kinds of wood early in the start of the semester. I kind of moved all this up to the front. So we have the kind of plywood veneered panels, and you have different grades of those panels. If you have this linked, if you want to go watch how they construct those guys. And then if it's not veneered, it could be fiberboard, particle board, wafer board, which is what they used to call OSB. I forgot about that actually. So oriented strand board. Here we go. Here's OSB. You'll see this a lot in the floor diaphragm or the sheathing system for floors, and as well as roofs and siding. There's a lot of my house. I've mentioned before, we've been working on the siding, and I've also myself been working on the floors, and that's what you'll find underneath. In my case, the outside pieces are rotten, and we're having to replace a lot of it. There's grading associated with panels, just like there is for glue lambs and some of our other wood components. There's structural pieces for these sheathings. We're not going to go through that. That's something you'll forget by the time you need to use it more than likely, but it's available in the slides here. So plywood sheathing, you can use it for roofs and floors to resist both gravity loads and lateral loads, but they're part of a system of 2x4s and studs and things like that. Okay, structural panels. There is span tables and design tools in the NDS. Okay. There's also the APA structural use panels. So, and there are nailing requirements depending on the demand. So a lot of times you just see someone shooting nails and such. There is a minimum number that has to be done to make sure that that load is transferred. So we're really looking for structural uses. It gets a little bit we'll get a little bit more precise on making sure that happens. Now, most of the standard practice when you see someone building a house, a contractor building a house, typically you'll see them use a lot more nails than they need with misses and things like that. But there is a minimum so that these things can transfer load. Here's some of the examples of different ply. Three layer, three ply is more typical. You can get even 5 and 7 layers, but those are not as common. But those become very significant structural panels. Okay, right. So this is how the system would work. Design Resources, NDS Chapter 9. Okay, so you've been introduced to the NDS at this point. The NDS has some good information. Don't forget the commentary in the back to read through this. And if you pick up a wood textbook, you will also, or honestly go into the wood resources for the Wood Council, which I'll give you that link. All right, we're not going to do these guys. Structural wood diaphragms, I'm going to just show you here on a picture what I'm talking about. And this is, if you think of the floor system to be able to translate the load. Okay, the floor, if here's my wind loads coming from this side, will want to bend in plane, but it's also, and then you have these collectors, which are along the edge, right? And those, so that kind of stiffens up the edge here. Likewise, in this picture where it's coming from this side. But the key here is that your floor diaphragm is used to transfer that load, and it provides some lateral resistance if we've got some of these, if we've got some stiffness here, right? But it's going to transfer the load through the diaphragm, okay? Deflection calculations, you don't want to have, so you assume that it's a flexible, not rigid diagram. It's not moving in one piece, it's bending like shown in the picture. You want to calculate that, but it shouldn't be too extensive based on the fact that we're loading it in the in plane direction and if we have the collectors and have it well put in place. All right. Let's move. Actually, here's showing you what it looks like. So you'd have your panels, right? You have each of these panels and they're staggered. This looks like a brick wall, but it's actually the OSB or structural panels laying in plan. All right. So taking it a step further, let's look at shear walls. So these are specially designed walls. So the diaphragms and the lateral resisting walls and things like this are typically what we need for a house. That's fine, or light commercial. If we have all that load being concentrated into a set of walls specifically designed to resist those forces, we call that a shear wall. So you can think of it as a vertical cantilever beam, like I said, like the elevator shaft or whatever, but you can do this completely in wood. So it's basically acting as a giant beam taking these big side loads. It's a little easier when you think of like a skyscraper in this respect, but this is what a shear wall is. So it's relatively thin, or the width here is relatively thin and compared to the height, but this width also how wide your shear wall is how you also determine how much shear it can take from the lateral load. Even though it's longer than thick typically, that depends on your floor height and whether you have multiple floors, it's still going to be a lot more of a, even deeper than a deep beam, right? So bending in these guys, it's a shear wall because long skinny members are controlled by bending. This is a squatty member, right? So shear is going to be the controlling load in a shear wall typically. This shows you kind of what, so here's some little shear walls here, okay, in a garage where you've got to have these wide openings. And you can see here what happens when your shear wall doesn't do what it's supposed to under lateral load. And we've seen plenty of those. You can see them in barns and things out that don't have shear walls in them that are old. This goes through, it's fairly self-explanatory. One of the things you'll see is masonry is a really good use or a really good material for shear walls, right? So in masonry, we're not as much looking at, you know, the long beams and things like that. Masonry is really good, and we're going to cover that next, is really good for things like shear walls. And so you may have a masonry shear wall along with a wood frame building. Okay, but you can also have a wood shear wall. So commonly exterior stud walls, as we've already designed for some lateral load, do resist that piece of wind. Okay. There's lots of different types of shear walls. Some of them may have windows or holes in them, but you need a full height portion to count as a true shear wall. Okay. So that's why we like to put them around areas where I don't need windows. All right. So there's methods for dealing with this, and it talks about this in section 4.3 of your NDS to look at the deflection piece. You want to, you don't want to have excessive deflection in these, obviously. A lot of other non-structural pieces are connected to these walls. And here it says uploaded design, but if you get the textbook or you go onto the wood site, there's a lot of information examples for these. This is not something you're going to have to tackle until you do the PE, and even then, it just kind of depends on whether you get a shear wall versus one of the more common type of problems. All right. There's a lot on shear walls. Okay, we are going to go into fasteners next, but I'm going to stop this video so we can do this one clean from the start.